So this unit is all about understanding what a function is looking like. After getting through this unit, we should be able to graph a function fairly well without using a graphing calculator, just by understanding derivatives and what signs of derivatives can tell us about a function. Last class, we discovered that the sign of the first derivative of a function tells us if the original function is increasing or decreasing. Okay, and that's how we turned critical points into locations of maxes and mins. That's how we discovered if a critical point was the location of a max or min. Today, we are going to be talking about a second derivative and what a second derivative can tell us about our function. Now, what was one application of a second derivative that we've already talked about in class? Very, very good. Acceleration, because we start with position, its first derivative is velocity, its second derivative is acceleration. Think about things accelerating, right? The velocity is increasing, okay, right? Velocity increasing means velocity's derivative is positive, okay? Velocity increasing. Now, what would that look like in terms of a position? Position has to be kind of curving upwards, right? Kind of understand that curve. If velocity is increasing, like my position's got to be really shooting up. Well, that is an example of like concavity. And we will discover that a second derivative will tell us about the concavity of a function. There's two types of concavity. There's concave up and concave down. And these are functions that are like always concave up. It opens upwards, it's concave up. It opens downwards, it's concave down. A straight line, this is not in your notes, but please include it in your notes, has no concavity, no curvature. But functions aren't always concave up or concave down. They can change. For example, this function changes its concavity in multiple locations. So I have these dots located because it looks like this piece right here, this piece is like opening upwards as it's decreasing. So this is concave up and decreasing. This piece right here, it is opening downwards. So right there, we switch from being concave up to concave down. Then, after we hit this point, we go from concave down to concave up. And then we can see we're concave up increasing, concave down increasing, and concave up. Well, these points actually don't have concavity because it's a point where we are changing concavity. These are very interesting points that we call points of inflection, or POI for short. And POI stands for points of inflection. All right. Well, let's see. So I told you the second derivative is going to tell us about the concavity of a function. I bet you guys can take a guess as to like a second derivative sign and what it tells us. But let's just confirm here. Here's a function. This function is all concave up. Let's sketch the first derivative and second derivative of the function. Okay? We did this, remember back in Unit 2. We would look at the tangent slopes at different locations. We'd plot those tangent slope values. So this is a very negative value here. This is less negative. Okay, keep going. Go ahead and graph f prime. And then after you get f prime, graph f double prime. Okay, if you see you have like a 0 at 0, you have a positive, and then more positive, positive, more positive. It appears that f prime looks like this. Okay, the tangent slope generator for f is this straight line. Now I could do a sign analysis just so that we know and remember that we can do sign analyses of the graphs of f prime. We see we have a 0 at 0. Okay, there's 0 right there at 0. The f prime values are negative to the left of 0. They are positive to the right of 0, which is telling me that f is going to be going down, then up, which we can see here. The function goes down, then up. Okay. Now, if we graph the second derivative, we look at the slopes of the first derivative. Positive slope, positive slope, positive, positive, positive. So it looks like we are positive and staying positive. Now, if I do a sign analysis for my second derivative, I see that the signs of f double prime are positive everywhere. What do you think the connection is? If it's concave up, the second derivative is positive. That's the key. So knowing that a second derivative is positive, I'll be able to say that my function, my original function, is concave up. All right. Well, you can go ahead and make an assumption about what's going on with something that is concave down, but let's go ahead and just double check. Do you need another packet? Okay. I got extras. So positive, less positive, 0, negative, more negative, positive, less positive, 0, negative, more negative. I looked at a sign analysis of f prime. Again, I'd see I have a 0 at 0. But I'd be positive to the left of it, negative to the right of it, which is telling me that f is going to go up and down. Yep, that's true. F goes up and down. Second derivative, all the slopes of these are negative, so we are going to be negative and consistent. If I threw down a number line and looked at the signs, second derivative is negative. So if a function is concave down, its second derivative is going to be negative. Okay, now what if you change concavity? What's going to go on with the signs of our second derivative there? Well, let's find out. Graph f prime, f double prime, and then do a quick little sign analysis of f double prime in this situation. Because we can see this function right here is concave down. It's opening downwards. Then it opens upwards, so this piece right here is concave up. So it looks like this function changes its concavity. Well, let's look. Positive, less positive, 0. Positive, less positive, 0. Positive, more positive, more positive. Positive, more positive, more positive. There's f prime. If I were to do f double prime, we would have this graph, which we've already done. Now let's look. If I did a sign analysis of f double prime, I see I have a 0 at 0. What are the f double prime signs to the left of 0? Negative. To the right of 0, they are positive. Well, is f concave down to the left of 0 and concave up to the right of 0? Yes. Concave down and then concave up. And since we've switched concavity, it looks like our sign of our second derivative switched. This must be a point of inflection. Well, we can see right here at 0, it would be a point where we change concavity. It would be a point where we did not have any concavity. We're changing concavity. Okay? This is how we are going to determine the curvature of graphs. We are going to look at second derivatives. The sign of a second derivative tells us the concavity of whatever we're looking at. If the second derivative is positive, I don't want to write f double prime because we might be asked about the concavity of just anything. Like, when is the velocity concave up? Which means you'd have to look at the second derivative of velocity, which is like the derivative of acceleration. So let's not keep f double prime as always being the second derivative. There could be other types of second derivatives. So when the second derivative is positive, we are concave up. If the second derivative is negative, we are concave down. If the second derivative is 0, we do not have any concavity. Points of inflection will occur when the sign of our second derivative changes. Okay, we'll come back and we'll talk about the second derivative test in a little bit. Let me give you a function. X to the fourth minus 4x cubed. I want you to determine the concavity of the function. One is the function concave up, one is the concave down. Identify the points of inflection and do that. Our goal, our end goal, is to produce a sign analysis of f double prime. In this case, that's the second derivative of f. Okay, discuss with your neighbors. How would we get there? How can we find a sign analysis of our second derivative? Discuss. We would basically be doing what we did to find maxes and mins, only with our second derivative. Some students are like, okay, well, I know how to find a second derivative. Just take a derivative of the derivative, right? But then it's like, when is this positive and negative? And all of a sudden they just forget. What separates positive and negative values typically? Zeros. Okay? So remember, how do you find if something's positive or negative? Find the zeros. Which is just like how we, found critical points. We just took the second derivative now. We're going to see when this is 0 or undefined. I say find the zeros, but it is find the zeros or see when it's undefined, because we can change signs at an undefined point. You get 0 and 2. Those get plopped down right here. And now we do our sign analysis. We know since we found all of the zeros that all we need is one test point inside our interval or outside of our intervals to know all of the signs of all of the points in those intervals. Plug in something like 3, positive times a positive, positive. Plug in something like 1, positive times a negative, negative. Plug something in like -1, negative times a negative, positive. Now this is not telling me that we're going up, down, up. It's different. This is the second derivative. This is telling me that f is concave up, concave down, concave up. Okay? Changed it up a little bit. Sign of a second derivative tells us the concavity of the whatever we're looking at. All right, so the original function f is concave up from negative infinity to 0 and from 2 to infinity. You can write that like that using that notation, or you can say x is less than 0 and x is greater than 2. F is concave down from 0 to 2. You can write it like that, or you can say from 0 to 2. We have points of inflection where the concavity changes. The concavity changes at 0 and 2. Cool? Cool. Well, next one. Let's just find the inflection points for x to the 5th plus 5x to the 4th. Change from what you have in your notes to this one. Okay, here's where some people mess up. They find the second derivative. They're like, oh, points of inflection, that's the zeros. That's when they change sign. They have 0 and -3. They circle that on a multiple choice test, and they are wrong. It's not that they're all wrong. It's that you got to do more work, okay? 0 and -3 are possible points of inflection. Just like when we found critical points, they were possible maxes and mins. The same goes with points of inflection. Don't stop here. Do the analysis of the signs of your second derivative. Because of this x squared, we notice that we're not going to change signs at 0. Let's see what the signs are. If I plug in something like 1, positive, positive. Something like -1, positive, positive. something like -4, positive, negative. That is telling me that F is concave down, then concave up, then concave up. We will not have any concavity at -3 and 0, but only x equals 3, -3, is a point of inflection. Now, how can you go from concave up to no concavity to concave up? Wouldn't it just be like concave up? Think about that for a second. How can you go from concave up to no concavity to concave up? Don't expect you guys to know this, but it might make sense to you if you look at two graphs. Let's look at the graph of x squared and the graph of x to the fourth. What does x to the fourth look like? Just like x squared, it's just a little bit slimmer, but there's a little bit more to its slimness. Okay, so there's x squared, x to the fourth, and maybe I should actually break out the calculator for this. Break out Wolfram. Actually, I think Wolfram's going to be better. All right, this is a great picture of what I'm trying to describe here. Okay, notice x squared looks like this, and notice how we're zoomed in between like -1 and 1, okay? And you see how x squared is nice and curved, right? Well, x squared is concave up everywhere. How do you know that x squared is concave up everywhere besides just looking at it? Because the second derivative is always positive. What is the second derivative of x squared? 2. Okay? F prime is 2x. F double prime would just be 2. 2 is a positive number, which means this is concave up everywhere. Okay? Now, x to the fourth ends up being slimmer, but notice, and you can see it on the picture, it flattens out. Okay, see x to the fourth comes down and it really flattens out. Okay, well, let's look at the second derivative of x to the fourth. So it's 4x cubed, and then it is 12x squared. Is this positive everywhere? No. It's positive everywhere except for 0. At 0, it's 0. So it's positive to the left of 0. It's positive to the right at 0, but at 0, it's 0. So here's a situation, x to the fourth, where you can go concave up to no concavity to concave up. Because, and look at the graph, you can see it, you flatten out so much that at this point, it's almost like we have a straight line down at the bottom. You see that? Flatten out so much, we have no concavity here, but then we pick up concavity afterwards. Pretty cool. So, moral of the story is, check your possible points of inflection, because it might not be a point of inflection. Okay, great. Now, what if I asked you, after you've done all of this work, to find the extrema? Now, don't do anything right now. I just ask you to find the extrema. Now you're like, oh man, now I have to like set my derivative equal to 0. I already did a sign analysis, but if it's for the second derivative, I don't want to do another sign analysis for the first derivative. Okay? I'm tired of it. Well, I'm telling you that you don't have to. Let's find the zeros for, I'm going to do this in blue, that way we know that this is separate. This is for the previous problem. I'm going to find the zeros for f prime. Okay? I'm going to go ahead and factor out a 4x squared. And I get x minus 3. And I get x equals 0 and 3. Okay? Now, if I focus on just 3 right here, by looking at the signs of my second derivative, without doing a sign analysis of the first derivative, like we did on our quiz in last class, which is the first derivative, I can tell whether 3 is a max or a min. By looking at the sign of my second derivative, I can tell if this critical point 3 is a max or a min. Discuss with your neighbors, is 3 a max or a min, and why? What is the concavity of my function when x is 3? Concave up. If we have a horizontal tangent, which is what we do, but your graph is concave up, how does that appear? Like that. 3 must be a min. Now what about 0? That's a very good question, right? This process that we just did, looking at the signs of my second derivative to determine if at critical points we have maxes or mins, it's called the second derivative test. It is not super important. I prefer us, because we do have some situations like at 0, I don't know, go from concave up to concave down. Is it a max, is it a min? Well, it could be anything, okay? In this situation, we would not change signs of my first derivative at 0. This would be a location of a neither max nor a min, okay? But when we look at our second situation, I'll show you how it's going to be a min. But this is the second derivative test. At a critical point, if you know the sign of the second derivative, you can tell whether or not the critical point is a max or min. Okay? If, let's say we have a critical point at x equals c, if the second derivative of c is positive, we know f is concave up, critical point, min. If the second derivative is negative, we know that f is concave down. At a critical point C, if we are concave down, max. Now we have a situation with like that 0. If the second derivative equals 0, just do the first derivative test. We don't know. Okay. So let me just show you exactly what's going on in this situation. If I did a sign analysis for f prime, I'm going to just throw it right on top of here. We got 0 and 3. I'm going to put 0 on top of 0 and 3 over here. I know we're going to be positive, negative, negative. So this is a neither, this is a min. I already knew it was a min because I looked at the sign of the second derivative, right? I already circled min, did that, okay? This confirms it. This also confirms that this is a neither, and it's not a max or min because I didn't know what the sign of my second derivative was. Let's go back to the second example. Let's look at maxes and mins for the second example. I don't know, you don't have any space, but whatever, just follow me. Follow me to freedom. We have 5x cubed times x plus 4. We get x equals 0 and negative 4. One of these, I know right now whether it's a max or a min. Discuss with your neighbors. Which one do we know is a max or min without doing any sign analysis of f prime? Gosh, you guys are good. At least those of you who quickly answered. Those of you who didn't quickly answer. We look at 0. The sign of my second derivative is 0, 0. I don't know. We look at negative 4. The sign of my second derivative at negative 4 is negative, which means the original function is concave down. Concave down at a critical point must mean it's a max. Must be. Well, let's confirm it's a max. At negative 4 and at 0. All right, I plug in something like negative 5. Negative 5 cubed is a negative. Negative 5 times 4. Negative 5 plus 4 is a negative. So this is a negative times negative, which is a positive. Plug in negative 1. Negative 1 cubed, negative. Negative 1 plus 4, positive. So this is a negative. I plug in something like 1. 1 cubed, positive. 4 plus 1, positive. So this actually, we knew was a max. And this is confirming that it's a max. Because I know that f is going up and then down. But look at 0. Well, we had a 0 here, we didn't know. But this is one of those situations like x to the 4th where we flatten out, but then we go right back up. So this is actually the location of a min, which is showing you the second derivative, not all that great. Cool? But we have to know it. Min. Okay? So don't rely on the second derivative, and don't make a guess like if the second derivative is 0, oh, it's going to be a neither situation. Nope. Could be a min. Could be a max. Fantastic. Oh, let's look between 0 and 4 pi for cos x minus x. You guys have this in your notes? No? Oh, you lucky dogs. Let's just keep going then. Okay, let's read the question. What is f increasing and concave down? Okay. Please discuss with your neighbors. How can we tell if a function is both increasing and concave down at the same time? Go. If we said, well, don't I have to look at the signs of my first derivative to tell if we're increasing or decreasing? And don't I have to figure out the signs of my second derivative to tell if we are concave up and concave down? And wouldn't I just look at those at the same time? You are correct. You can't just figure out if something's increasing or decreasing based on the second derivative. You can't. You can tell if you're concave up or you can tell if you're concave down, but you could be concave down and increasing. You could be concave down and decreasing. You could be concave up and decreasing, concave up and increasing. So we just have to do both at the same time. Let's go ahead and do that. You're going to have to take the first derivative. You're going to have to take the second derivative. You're going to have to look at signs for both. It means you have to find the zeros or when they're undefined for both. I'll leave the sign analysis to you. Check your answer once you think you have it. Hold on. Yeah, you got it. Everything was correct. You got it? Nice. You got it. Okay. What's this for? Okay. 0 to 2, it's increasing. Okay. What this is for? Okay. Yep. So I want to be both this and this at the same time. I want to be increasing and concave down at the same time. So you already told me this is when we're increasing.
Yeah.
When are we concave down?
Like greater than 1?
Yep, over there.
Yeah.
Where do they overlap?
2? Or would it have to be like 1.5?
Between 1 and
okay.
2.
Okay.
Right? Right where they you got it. You had it.
So then we have to take both of these.
Yes, it's best if you have the signs down on top of each other. Okay? If you know that this is a negative, a positive, and a negative, this is a negative and a positive. This is telling me F is going down, then up, then down. This is telling me that F is concave up and concave down. We need the overlapping area. The overlapping area when we are increasing, which is right here between 0 and 2, and concave down, which is from 1 to infinity, is just from 1 to 2. That's when my first derivative is positive and my second derivative is negative. That's it. Okay? Great. Moving on. Now, just like we did to find maxes and mins, we have these situations when you're given the graph of f prime. And you are now going to be asked about the concavity of f, the original function. Okay? The question is, where are the inflection points of f? And just analyze the concavity. Let's throw that one in there. Now, if you say, oh, Mr. Messner, there's no inflection points, this graph is concave down everywhere, you're wrong. You are wrong. Just like we did for f prime and finding maxes and mins off of a graph of f prime, we need to turn this two-dimensional f prime graph into a one-dimensional sine of f double prime graph. Now, let's think about this. We all can do this. This is f prime right here. I want to know the signs of f double prime. Are they positive? Are they negative? Are they zero? What's going on? What do you have to look at on the graph of f prime to figure out the signs of f double prime? Discuss. Okay, let's think about this if we didn't talk about the S word, because the S word is the important one. Okay. What's the relationship between f double prime and f prime? The derivative, okay? So the derivatives of f prime gives us the values of f double prime. What's another word for derivative? Slopes. Slopes of what? Tangents. To find the values of f double prime, we need to look at the slopes of the tangents to f prime. So even though I wrote down f double prime, I am thinking and I'm looking for the slopes of f prime. Now again, separating positive slopes from negative slopes are what? Zero slopes. Here is a zero slope right there at 0. So I'm going to throw 0 down. To the left, what are these slopes? Positive slopes. They're going up from left to right. To the right, what are these slopes? Negative. This is telling me, oh, that's a funky negative. This is telling me f, the original function f, is concave up, then concave down. We have a point of inflection at x equals 0. We are concave up when x is less than 0. We are concave down when x is greater than 0. Understanding that we are talking about f, not f prime. You know, f's point of inflection, which we can't see, we don't know, is at 0. F's concave up when x is less than 0. F is concave down when x is greater than 0. Okay? Great. Look at the graph of this f prime. Tell me, where are the inflection points for f? Go discuss that with your neighbors. Now, if you say negative 2, 1, and 3, you are wrong. What we all should be doing, what we all should be creating, even though we might be able to see the answer right away, because this is going to help us for our second part, is a sign analysis of our second derivative. And to find the signs of our second derivative, what do we look at on my first derivative graph? Slopes. Start with the zeros. When is the slope 0? Here and here. To the left of the zeros, slopes are positive. Between the zeros, slopes are negative. To the right of the zeros, the slopes are positive. The inflection points, therefore, are at -1 and 2. Next level question. When is the original function decreasing and concave up? Discuss how you're going to figure that out. Now, here's the answer. Here's the answer. And you might be able to get the right answer, but here's what I want to see from all of you. I want to see a number line sign analysis for both f prime and f double prime. Just like when I asked you to find the maxes and mins and I gave you a graph of f prime, I wanted you to get this down. Now, since I'm asking you about decreasing and concave up, just do the number line analysis. All the information will be in there. You will be able to answer any question that I give you if you do a number line analysis for f prime and f double prime. Now we got to think back to our quiz today and our lesson last class, f prime signs. Now we are looking at the zeros for f prime, just like we did for our quiz today. And then we look around our zeros and between our zeros for our signs. Could you look at the graph and get the correct answer? Sure. But boy, would I prefer you do this and then think, okay, decreasing, that's here, concave up, that's here. Here is one location where they overlap. Here's another location where we're decreasing and concave up, right there. And it's because you are thinking, okay, f prime is telling me that f is going down, then up, then down, then up. The second derivative is telling me that f is concave up and concave down and concave up. Okay, next problem. I'm going to switch this up on you, but don't worry. Did we have any questions on the last one? I'm sorry, I kind of rushed there. We should be from negative infinity to -2 and from 2 to 3. Two intervals in which we are both decreasing and concave. Okay, next problem. Changing it up on you a little bit. I'd like you to pretend like there's a sharp point there. Okay, so just kind of like connect your things, sharp point. Okay, sharp point there. Please tell me what the inflection points of f are, and then please tell me when is f increasing and concave down. Tell me. Let's look at our second derivative signs. What is the second derivative sign at 2? Is it 0? No, because it's a sharp point, right? What's the derivative at a sharp point? Undefined. Well, when we're finding critical points, we look for when our derivative equals 0 or is undefined, right? So this is a location of what we can call a critical point for f double prime. The slope is undefined. Okay, that's fine. Look to the slopes to the left of 2 and to the right of 2. Positive slopes, then negative slopes, which means F goes from concave up to concave down. Now, don't ask me what the graph of F looks like here. Okay? Where the derivative is going to be positive, but the second derivative is undefined. Don't ask me. Maybe it's like I don't know what it's going to look like. Okay? Just go with the fact that the graph is telling you F is concave up and concave down. There is an inflection point at 2. Even though it's a sharp point, it is where the concavity is changing. It's where the signs of the second derivative change. All right, now answer the second part. When is F increasing and concave down? Wait. Yep. Nope. Nice. Excellent. We're on top of this. You got it. That's it. You did it. Yep. Good. We're good. We're good. Yeah. This is correct. That is correct. Put them together. I'm not looking over your shoulder. Never mind. Let's see. F prime is negative until 0. It is positive until 4. It is negative after 4. F is increasing when F prime is positive. That's here. It is concave down when F prime is negative. F double prime is negative. That's here. Where do they overlap? Here. That is from 2 to 4. We did it.